So back in Calculus 1, you learned how to do linear approximations to approximate values of functions given a derivative or some other information about a function and its derivative. And you use that to approximate something. So let's say you have the function f of x is equal to the square root of x. Well, you were given this function, and based on what you knew about f of, let's say, 9, which is equal to 3, you were approximating f of 10, which is, what is the square root of 10, right? And without this notation, you were essentially if let's say you didn't know what, root 10 was, well, we can guess it and we can approximate what f of 10 would be using linear approximations. And the idea of that would essentially be like if you had a tangent line on some point, let's say this is the point that we start at, and this is the point that we want to know, right? So we know what this value is. We know this value is at 9, and it's 3. Well, we can use a tangent line at that point to kind of guess that, this is pretty close to the actual, right? These two don't have that much of a big difference. So we can use this point from the tangent line to kind of guess where what value of that function is. Well, we're going to use a similar idea, and it's going to be called Euler's method. And say you are given a differential equation like this, dy dx is equal to xy, and you're given an initial condition, y of 0 is 0, and we want to know what y of 1 is approximately, and we can use all of this information here to figure about what this would be. And the idea here is that if you have some function, again, that to get from this point to this point right here, we're going to be constantly using the tangent line, the change in y over the change in x, again and again, like that. So let me make this more clear. It'll be, we're going to find dy dx, and we're going to take step sizes. So we're going to take maybe 1, 2, 3, 4 step sizes, and we're going to use the tangent approximations each time to keep guessing and closer using the derivatives known at those individual step size points, those ticker marks, to kind of get to this until we get to this final point that we want. Okay, so Euler's method is done in various different ways. The way that I do it is by simply memorizing a formula. So the formula is that the next prediction, y sub 1, is equal to y sub 0 plus h dy dx at y sub 0 or x sub 0, y sub 0, okay? So this is the formula that you're going to want to know. Another way to interpret this, and h is the step size or delta x, and y sub 0 is the initial condition. But more importantly, the thing that you want to really get is that this is essentially the formula that you really want to know conceptually is this one. Because it's saying that the next term is always given by the previous term's initial value plus the step size times the derivative at the previous coordinates you were given. Okay, so the idea is we're going to do this on and on and on until we get to our desired, let's say y sub w is the value that we want to get. So we're given y sub 1, is equal to something, so we want to find y sub w. Let's say y sub 1 was 1, and we want to find y sub w is that. We're going to use this sequence of recursive formulas to get to y sub w. You'll see how this all works out, but these are the formulas that you really want to know. Okay, so back to that problem, dy dx is equal to 2xy. I'll make this a little bit fancy for you guys using math conversions. So this is the problem that we want to solve. Okay, and we're given that y sub 0 is just 0. Okay, so that means that y0 is 0 and x0 is 0. Okay, so these are the initial conditions. By the formula, y sub 1 is equal to y sub 0 plus h dy dx at x0, y0. And I want you to approximate y sub 1 using two step sizes. Okay? So the first question here is, okay, well, if it's two step sizes, how do we get from 0 to 1 in two equal steps? Well, you just add the two and divide it by, add the, number 0 and 1, right, from 0 to 1, and just find the average. And that's going to be 0.5. This is your step size. The average between your two initial your initial x coordinate and the predicted desired x coordinate, the average of those will be the step sizes in this case. However, if you want more step sizes, you would essentially change this bottom into, let's say you wanted 4, you would just divide it by 4, okay? But in this case, we want 2, so it's going to be 0.5. All right, so plugging in what we already know, we know that y sub 1 is just simply y sub 0, which is 0, plus x, h, which in this case is just 0.5, times the derivative at 0, 0. And the derivative at 0, 0 is just 0. So y sub 1 is actually just 0. Well, that's pretty neaty. Okay? And remember, now this means that x sub 1 is 0.5. We moved one step by 0.5. Remember, we started at, x equals 0. Started at x equals 0, then we went to 0.5, so now we're here, and we know that this point right here, this y-coordinate, is at 0 as well, which is not drawn correctly at all, but you get the idea. Okay, so now we want y sub 2, which is equal, so we want y of 1, which is approximately y sub 2. That's what we want to know. And this is equal to y sub 1, which is 0 again, plus 0.5, the step size, times the derivative at 0, 0.5. This was from the previous coordinate system, right? So we put those here. Sorry, it's not 0, 0.5, it's the other way around. 0.5, 0. And once again, this is just 0, so this is 0. So y sub 2 is 0, and y sub 1 is therefore approximately 0. Okay. Let's do another problem. So we're given dy dx is equal to 2x plus y. We're given that y sub 1 is equal to 1, and we want to know the approximation of y sub 0. Okay, similar step process here. Now, of course, this was very convenient that y sub 0 was 0, which would make the derivative always 0. And in fact, if you looked at a slope field of this, the horizontal x-axis would all have slopes of 0. So every point of 0 would be 0. In this case, we're going to go backwards now, okay? Now, here's the only thing different. In this case, the only thing you have to know is that y sub 1, or the next term, is simply y sub 0 minus h dy dx at x0, y0. It's just minus, because you're going backwards now, okay? That's all that matters. So let's do it. So f, and a good way to really understand this is, okay, we know that y of 1 is equal to 1. We want to know now using two step sizes, okay? Two step sizes. Which means that it's just, once again, the step size is 0, but it's negative this time. So y sub 1.5, or sorry, y sub 0.5 is the next step that we're going to look at, is approximately y sub 1, which is equal to y sub 0, or sorry, y sub 0, which in this case is 1. Remember, it's just 1 minus 0.5 times the derivative at 1 comma 1. Okay? And the derivative at 1 comma 1 is just 3. And so it's 1 minus 0.5 times 3, which is negative 0.5. Okay? This is y sub 1. So y sub 1 is equal to 0.5, and x sub 1 is also 0.5. Sorry, y sub 1 is negative 0.5. And now what we're looking for, y sub 0 is then approximately y2, which is equal to y1, which is negative 0.5 minus 0.5 times the derivative at 0.5 comma negative 0.5. And this is where the math gets a little annoying, especially for the APA test. But it'll just be negative 0.5 minus 0.5 times, plug in 0.5 for both of these. We will simply get 1 minus 0.5, which is 0.5. And from here, it's negative 0.5 minus 0.25. And this is negative 0.75, which is the approximation that we're looking for. Okay, so this is it. That's all you need to know about Euler's method. Memorize this formula, and yeah, this is essentially it. Of course, there are times where they're going to ask for 4 step sizes. Just remember, if it's 4 step sizes here, we would just take 1 plus 0 divided by 4, and each step size would be 0.25. Okay, so that's it. And just make sure you be really careful with these calculations. And that is all we're going to cover for this video. Stay tuned for upcoming videos on tutorials helping you guys for the AP Calculus exam. See you guys later.